All right, hello, welcome to Thursday. Um, we are continuing talking about problem solving. Today is a special form of motion, a special case, if you will. So the special case we're going to talk about is called free fall. So we're going to talk about what free fall is and how we use it. So first thing is a warm-up. So I'd encourage you to do this in your notebook. Consider it a practice problem. So go ahead and pause, do this problem, and then see if you get what I get. Okay, so let's see. First thing, draw some kind of a diagram, not just a fun picture like is there. List all of your knowns and unknowns, and then decide which equation you're going to use. Well, we don't have a final velocity, so we use the equation, the 1/2 at squared equation, because we don't have final velocity. From there, you substitute everything in and solve carefully. Now you'll notice I left everything in centimeters, and that's fine because everything was in centimeters. Centimeters per second squared. So as long as everything is in the same units, you can leave it. The only place you have to be careful is if there's meters and centimeters, then you have to convert. So if we had been in class last time, I would have had you do a lab with picket fences. That's where you would have dropped things and you would have measured accelerations. And when we did this back in the fall, these were some numbers that the lab groups were getting. And one of the things that I had you do is throw it down or throw it up. And what we noticed was that that the initial velocity might have changed, but it did not seem to affect the acceleration. And that's because everything falls with the same constant rate because of gravity. So this brings up this concept of free fall. All right, free fall refers to the motion of an object determined solely by gravity, free from all other forces. So basically anything that's falling, anything in the air that is not self-propelled or have significant air resistance is going to be in free fall. So dropping your phone on the table, jumping out of a window, throwing a baseball up in the air, all of those things are considered free fall. Galileo was the first one to really state this. He used to go up on the Leaning Tower of Pisa and drop stuff. People thought he was crazy. He probably was, but he would drop all kinds of stuff, and he was the first one to conclude that all objects fall at the same downward acceleration if we can ignore air resistance. And here on Earth, we use acceleration due to gravity as negative, because it's going down, it's accelerating downward, as negative 9.81 meters per second squared. And we're still going to use the same equations that we have been using. All those equations of motion that we've started using, we're going to use the same equations still. The only difference is that if it's dropped, then the initial velocity is 0. And also, if it's in free fall, it might not tell you to use gravity. You'll have to remember to use that. So let's do a little example problem. So we got Wile E. Coyote here, good old classic cartoons, and he is trying to drop a boulder down onto the Roadrunner to try and catch the Roadrunner once and for all. And if we want to say the cliff is 132 meters high, the question is how long, meaning time-wise, will it take for the boulder to reach the ground? So if you look at this, the only thing we're given that were stated directly is that it's 132 meters high. It's the only thing. So first, draw a picture. And again, the only thing we're given is that it's 132 meters high. And you might be like, well, I'm not going to be able to figure out much. But there's a couple things that are implied. If it's being dropped, then your initial velocity is 0. And because it's falling and everything falls at the same rate, then your acceleration is negative 9.81 meters per second squared. And we're looking for time. So very similar to the initial problem that we did, we don't have final velocity, so we're going to have to use the 1/2 AT squared equation. Since the initial velocity is 0, that last term goes away. And we substitute in and solve for time. So the Roadrunner would have about 5.2 seconds to get out of the way after he sees it. It's quite a bit of time to move out of the way. All right, here's one for you to do on your own. Try this. I didn't do this on the computer last semester, apparently, so I had to do it on paper. And so, first thing is draw a picture. So I got this phone falling down to its watery depth. List my knowns and unknowns. So I've got delta x, I have acceleration, initial velocity, I don't know time, and I also don't know final velocity, so that leads me to use the 1/2 AT squared equation again. And we substitute everything in and solve for t. So make sure you solve carefully. Leave that t squared for last. And then at the very end, you would square root both sides to get your final time. Make sure you leave that t squared for last. All right, that's it. Short little lesson. We would have done a little activity worksheet, which I posted to Classroom, so I would like you to do that. And then there's your homework. So that's it for this week, and I will see you next week.